To determine the maximum load a parallel transformer bank can withstand, we need to follow a step-by-step approach. The example involves two transformers in parallel. Transformer A and Transformer B. Transformer A is rated at 1000 kVA with a 4% impedance, and Transformer B is rated at 2000 kVA with a 6% impedance. Firstly, we need to convert the kVA ratings of the transformers to MVA. For Transformer A, the kVA rating is 1000 kVA. To convert this to MVA, we divide by 1000. So 1000 kVA divided by 1000 equals 1 MVA. For Transformer B, the kVA rating is 2000 kVA. Converting this to MVA, we divide by 1000. Therefore 2000 kVA divided by 1000 equals 2 MVA. Secondly, we need to calculate the per unit impedance for each transformer. For Transformer A, the impedance is given as 4%. To convert this to a per unit value, we divide by 100. Thus 4% divided by 100 equals 0.4 per unit. For Transformer B, the impedance is given as 6%. Converting this to a per unit value involves dividing by 100. So 6% divided by 100 equals 0.6 per unit. Thirdly, we calculate the equivalent per unit impedance of the parallel combination. The formula for this calculation is C equivalent equals C of A multiplied by MVA of A plus C of B multiplied by MVA of B divided by MVA of A plus MVA of B. Plugging in the values, we get Z equivalent equals 0.4 multiplied by 1 plus 0.6 multiplied by 2 divided by 1 plus 2. Simplifying this, we have Z equivalent equals 0.4 plus 0.12 divided by 3. This further simplifies to Z equivalent equals 0.16 divided by 3, which equals 0.533 per unit. Fourthly, we calculate the maximum load in MVA that the parallel transformer bank can handle. The formula is MVA maximum equals 1 divided by Z equivalent multiplied by MVA base. Here, MVA base is the sum of the individual transformer MVA ratings. MVA base equals MVA of A plus MVA of B, which is 1 plus 2, equaling 3 MVA. Therefore, MVA maximum equals 1 divided by 0.533 multiplied by 3. This gives us MVA maximum equals approximately 18.76 multiplied by 3, which is approximately 56.28 MVA. Fifthly, we convert the MVA maximum back to kVA. To do this, we multiply the MVA maximum value by 1000. kVA maximum equals MVA maximum multiplied by 1000, which is 56.28 multiplied by 1000, giving us 56,280 kVA. Therefore, the maximum load that this transformer bank can withstand is approximately 56,280 kVA. Now, let's delve deeper into the concepts and calculations involved in determining the maximum load a parallel transformer bank can withstand. Understanding these principles is crucial for electrical engineers and technicians involved in power system design and maintenance. Transformers are essential components in electrical power systems used to step up or step down voltage levels to facilitate efficient power transmission and distribution. When the load demand exceeds the capacity of a single transformer, multiple transformers can be connected in parallel to share the load. However, for parallel operation to be successful and safe, certain conditions must be met, including having the same voltage ratio, polarity, phase displacement, and impedance. The impedance of a transformer is a crucial parameter that affects how it shares the load with other transformers in parallel. Transformers with lower impedance will tend to carry a larger portion of the load compared to those with higher impedance. If the impedances are significantly different, it can lead to unequal load sharing and potentially overload one or more transformers, causing overheating and failure. The per-unit system is a convenient way to normalize electrical quantities, making calculations simpler and more intuitive, especially when dealing with transformers of different sizes and voltage levels. In the per-unit system, voltage, current, impedance, and power are expressed as fractions or multiples of a base value. This eliminates the need to deal with actual values that can vary widely depending on the voltage and power levels. The base values are typically chosen to be convenient round numbers, such as the transformer's rated voltage and kVA. Converting kVA to MVA is a straightforward process that involves dividing the kVA value by 1000. This conversion is often necessary when dealing with large power systems where MVA is a more convenient unit to work with. Calculating the per unit impedance involves dividing the percentage impedance by 100. The percentage impedance is typically provided in the transformer's nameplate and represents the voltage drop across the transformer at full load, expressed as a percentage of the rated voltage. The equivalent per unit impedance of the parallel combination is calculated using the formula mentioned earlier, which takes into account the per unit impedance and MVA rating of each transformer. This formula is derived from the principles of parallel circuit analysis and ensures that the equivalent impedance accurately reflects the combined effect of the individual transformer impedances. The maximum load in MVA is calculated by dividing 1 by the equivalent per unit impedance and then multiplying by the MVA base. The MVA base is simply the sum of the individual transformer MVA ratings and represents the total apparent power that the parallel transformer bank can supply. Finally, the MVA maximum is converted back to kVA by multiplying by 1000. This gives the maximum load in kVA that the transformer bank can withstand without exceeding the rated capacity of any of the individual transformers. In the example, the maximum load was found to be approximately 56,280 kVA. This means that the parallel transformer bank can supply up to 56,280 kVA of apparent power to the load without overloading any of the transformers. It is important to note that this calculation assumes that the transformers are operating at their rated voltage and frequency and that the load is balanced. In practice, these conditions may not always be met, and it may be necessary to direct the transformer bank to account for these factors. Additionally, other factors such as the ambient temperature and the transformer's cooling system can also affect its load carrying capacity. Therefore, it is always recommended to consult the transformer manufacturer's specifications and relevant industry standards to ensure safe and reliable operation. Furthermore, it's essential to consider the limitations and assumptions inherent in this calculation. Firstly, the formula assumes that the transformers have similar voltage ratios and phase angles. Significant differences in these parameters can lead to circulating currents between the transformers, reducing the overall efficiency and potentially causing overheating. Secondly, the calculation assumes that the transformers are connected to a common bus with negligible impedance. In reality, the impedance of the connecting cables and busbars can affect the load sharing between the transformers. Thirdly, the calculation does not account for harmonic currents, which can increase the losses and reduce the load carrying capacity of the transformers. Harmonic currents are typically generated by nonlinear loads such as electronic devices and can distort the voltage and current waveforms. In addition to the calculations, it's important to consider the practical aspects of operating transformers in parallel. One key consideration is the protection of the transformers. Each transformer should be equipped with its own protective devices, such as fuses or circuit breakers, to protect it from overloads and short circuits. These protective devices should be coordinated to ensure that only the faulty transformer is tripped, while the other transformers continue to supply power to the load. Another important consideration is the maintenance of the transformers. Regular inspections and maintenance are essential to ensure that the transformers are operating properly and to prevent failures. This includes checking the oil level and condition, inspecting the bushings and connections, and testing the insulation resistance. Finally, it's worth noting that there are alternative methods for calculating the maximum load of parallel transformers. One such method is to use a power flow analysis software, which can accurately model the entire power system and take into account all of the relevant factors, such as the transformer impedances, voltage levels, and load characteristics. Power flow analysis software can also be used to optimize the load sharing between the transformers and to identify potential problems such as voltage drops and overloads. In conclusion, calculating the maximum load that a parallel transformer bank can withstand is a crucial step in power system design and operation. By following the step-by-step approach outlined above and considering the practical aspects of parallel transformer operation, electrical engineers and technicians can ensure the safe and reliable operation of these essential components. Remember to always consult the transformer manufacturer's specifications and relevant industry standards, and to use appropriate protective devices and maintenance procedures. Always prioritize safety and adhere to established guidelines when working with electrical equipment. Continuous learning and staying updated with the latest industry practices are essential for success in the field of electrical engineering.